All right, so when we talk, yeah, sure, we talk about planes, right? And kind of told you when we talk about a plane, it's a flat surface, it's keyed, that extends in all directions forever, maintaining that that has no thickness. Okay. So when we talk about points that are all on a plane, okay, as a group we call them co-planar. Remember, co meaning together, and now that root word planar meaning plane. Okay. So if I'm dealing with something that looks maybe kind of like this, just can't see it yet. There we go. Still can't. There we go. So if I look at that orange surface, okay, we're considering that a plane. And they start to like change the shading towards the edges here to kind of infer that it's going to zoom out. It's going to go on forever. Okay, but there is no thickness to it, meaning that, you know, if I look at it from that angle, there's a lot of lag in my computer right now, so I apologize. If you look at it, kind of like it disappears, right? There's no thickness to it, okay? But those points that are on it right now, I've got A, B, and E on it. Okay, so those blue points are coplanar, okay? Any grouping of points that are in that plane are going to be coplanar. So it could be any 3 points, there's a plane that's going to go through them. So any 3 points are always coplanar. The question really comes into play when I start talking about a group of 4. Okay? Because if I look at A, B, E, and D, D is not in that group, right? D does not fall in that orange plane. So that group of 4 points is not coplanar. Okay? The only way that I could get D to be part of that orange surface is that if I get that surface to kind of bend down or dip down and go through D. Does that make sense, everybody? And then when I do that, when I bend that surface down to go through D, I violate what we've set up to be a plane. A plane has to be a flat surface. It cannot bend, cannot warp, and things like that. Okay? So I'll give you some examples of things that may not or are not planes. Okay? But they're surfaces. So if I go to, let's see if this will work. X squared plus okay, so that thing, that green thing, okay, kind of looks like a piece of paper that I've kind of just warped, right? Is that going to make sense? Okay, but it's not a plane, it's not flat. Okay, we just consider that a surface, and a lot of surfaces have some weird names. You don't need to know anything about surfaces right now other than planes. But here's another one that might be somewhat familiar to you. Okay, that green surface, we call that a paraboloid. Okay, kind of looks parabolic, doesn't it? Parabola. I saw those last year. Okay, but it's not a plane because it bends. Okay, it bends on itself. It curves. So not a plane. So when talking about planes, they got to be flat, and that idea, that concept, is what allows us to say that any 3 points are going to be coplanar. But when I'm looking at a group of 4 or 5 or 6 points, I have to make sure that they all exist in the same plane so they do get considered coplanar or not. Is that all right? If you've done your homework or looked at any of that, you're going to see questions that ask you, they give you a picture like this and ask you, is the group of points A, B, E, C coplanar? All right, all you got to do is check to see if all of them lie in the same plane that they've drawn out or not. Okay? So phrase non-coplanar is obviously the situation when the 4 or more points do not lie in the same plane. Is that all right, everybody? Okay. The idea, I think we talked about this yesterday. If we were to take 3, did we talk about me like raising my hand and 2 of you guys raising your hands and putting a piece of plywood on top of it or something like that? Okay. So these blue points are like our hands to give you maybe a visual. And I will never be able to move these 3 points in any fashion so that there's not a plane able to go through them. Does that kind of make sense? That orange plane is always going to be able to rest on those 3 points. Okay? And that idea tells us that to create a plane, that all we need is 3 non-collinear points. Let's see here. And the key concept is that 3 non-collinear points create exactly 1 plane. Okay, what I mean by that is that if I choose those same 3 points again, A, B, and E, and I get another plane to go on top of it, is that a different plane or is it still the exact same one? Okay, if I unhighlight it, highlight, so is it the same plane? Yeah, okay. So 3 non-collinear points create exactly or develop exactly 1 plane. So that gets us into this vocabulary word, and it's not so much that it's a huge vocabulary word in regards to it's mind-blowing or anything like that, but I'm going to use the phrase intersection or the word intersection quite a bit with you guys, and all that means is that it's the set of points that 2 shapes share, okay? Or 2 shapes have in common. You guys dealt with intersection of lines last year when you graphed 2 lines on a set of x and y axes, dealing with systems of equations, and you were looking for that ordered pair that both of those lines had in common, okay? Or the ordered pair that satisfied both the equations that you used. So you've seen the use of intersection before, and part of, a big part of this class is talking about how certain shapes intersect other shapes, and when they do that, what are the results of that? Okay, what are the consequences of an intersection? So as we go through the last 2 slides or 3 slides, that word's going to come up several times to make sure we're on the same page with what it is. Is that all right? Okay. So now we're going to bring into our geometry understanding another category of phrases or statements. Okay? We already talked about definitions and how we make definitions using previously known terms to create new ideas or new phrases to categorize or identify objects. Now we're going to talk about other types of statements that are not necessarily definitions, okay? But they're providing us information, providing us true facts, okay? And the first category of these types of statements are called postulates. Remember back to Wednesday, I think I introduced the guy named Euclid, okay? And he had 5 to 6 of these statements, these universal truths that because of them we're able to put them together and create new statements, and then put those together and create even bigger, newer statements, and that ultimately develops geometry for us. Okay? He called them axioms. Okay? Our textbook calls them postulates. Most high school geometry textbooks are going to use the word postulate. But it's simply a statement that we have to accept as being true without any proof. Okay? Remember me talking about what undefined terms were? When we come into class and we have no geometry background, we have no geometry words yet, clean slate of knowledge, we have to have some starting point, right? We have to have some words that we can use so we start talking about new things. And those words that we're going to start with were points, lines, and planes, right? Okay, those were the undefined terms. And then with those, we can start creating new definitions. It's the same kind of principle. If I want to start talking about some true facts and stuff like that, and all we have is nothing, we have no idea, no concepts of geometry yet other than a couple terms, I can't really start anything. I can't do anything. We need something to get the ball rolling again. All right? And these postulates are those statements that kind of get the ball rolling. All right? One of the big things about geometry, and what you find out ultimately about all of mathematics beyond geometry, is that we want to prove things. We don't want to just take somebody's word for it and just say, I'm happy with what they say, I think they're right, I'm going to go with it. We want to have the ability to say, okay, what did they say? All right, I'm going to have maybe some of my own doubts about that, and I'm going to take it the next level. I'm going to start doing some steps to say whether that is true or not. I'm going to see if I can go through a process that says, yes, that person is absolutely correct. Okay? It'd be like going into like a court case or something as a defendant or a plaintiff or something like that, and my lawyer not have a defense for me. Does that make sense? Okay? Maybe I'm being convicted of a crime and my lawyer has huge gaps in his case. That's not good for me, right? Okay? So basically he's going to go to the court and the jury say, he's innocent, he didn't do it. And that's his only argument. That's not a good lawyer, right? So in mathematics, we like to prove things. All right? And we're not going to just say, this is true because somebody told me. Okay? He's innocent because my lawyer's telling everybody that I'm innocent. That's not very valid. Okay? So in math, we like to prove things. We like to show why they are what they are, and there can't be any gaps. Okay? Because if there's gaps, somebody smarter than me might come along and exploit that gap. Okay? They might attack it and say, well, his statement is false because there's not a connection between these two things. There's a big gap. So we like to prove things. And the reason I'm talking about this is there are some things that we cannot prove. Okay? And those things that we cannot prove are called postulates. I told you the other day that Euclid had a handful. Okay? Our textbook takes his handful of postulates, or axioms he called them, and it breaks it down into about, I think we got about 25 to 30 of them throughout the entire year. Okay? We cannot prove them. We can draw pictures. We can kind of talk through, discuss them, maybe convince ourselves that yes, this has to be true. And somebody in the last class said, well, they're almost like common sense type things, and that's absolutely right. Okay? If we're talking about common sense, you usually don't have to prove yourself with common sense stuff, right? Okay? Everybody knows it, and everybody's going to agree that that's just the way it is. Okay? So that's what a postulate is: a statement, type statement that has to be accepted as being true without any proof or any validation. Okay? But one thing I want you guys to realize is that what I did with my PowerPoints, okay, is I like to take them out of textbooks instead of writing, retyping, and all that kind of stuff, as well as drawing the pictures that go with them. So I cut and paste these out of the textbook. Okay? This first one's called postulate 1.1 or 1-1. I don't want you to remember the names of these things. Okay? If I do want you to know the name of it, or I'm going to allow you to know the name of it, I will tell you. Okay? The reason I don't want you to do this is because postulate 1.1 is 1.1 for our textbook. For another textbook, it might be postulate 2.2. Okay? Or it might be another chapter, it might be 3, 4. Does that make sense? Okay? So these phrases, these 1, 1, 1, 2, 1, 3, it's an indexing for just this textbook and probably no others. All right? So if you get to memorize these things by those numbers, and then you get to a course, the next course in high school, and you need that stuff, and you're memorizing that as well, that's just postulate 1, 2. That course can have a prerequisite of geometry that uses the same textbook we did. Your teacher's not going to know what you're talking about. Does that make sense? Okay? And nowhere on the end of course exam, because the end of course exam is for the entire state of Ohio, and not everybody in Ohio uses the same textbook. So when you type in a proof, you have to write a paragraph proof to these people, and you say because of postulate 1, 2, I know this is true, they don't know what postulate 1, 2 is. They're going to know postulate 1, 2 as if two distinct lines intersect and they intersect exactly 1 point. So make sure that we understand that we're not memorizing them by their titles or their names. Okay? First one up there, through any 2 points, there's exactly 1 line. Through any 2 points, there's exactly 1 line. Okay? So hopefully you can write that down. I'm going to write something on the board next to it to kind of prove a point about the phrasing up there. I'm going to write through any 2 points there is a line. Only thing different, I took the phrase exactly 1 and I replaced it with the word or a. Okay? And that's the problem. The way I did that on the whiteboard, there's an issue there. Okay? Because when you guys know what ambiguous means before I use that word? Let's say I have a friend and their name is Pat. You know anything about Pat? It's a unisex name, right? It's a gender neutral name. Okay? Pat could be a guy, or Pat could be a girl. Okay? You know nothing about it. So their name to you or their identity to you is ambiguous. Some of you probably saw a guy show up in their head when I said Pat. Some of you saw a girl show up in your head when I said Pat. It can be left open to interpretation. Okay? That's what it means to be ambiguous. Okay? So this is ambiguous. There's some ambiguity in using that word a instead of exactly 1. Okay? So if I told you to hold your hand out, both your hands, and I put a line in your right hand and I put a line in your left hand, and you're holding them both in your hands, and I asked you, do you have a line? Do you? You have a line, right? A lot of us probably have 2 parents, right? If I ask you, do you have a parent? Answer that's yes, right? Well, some of us have 2. All right? So when I use the word I'm not being specific enough, because it means, or it leaves open to interpretation, that yeah, I've got at least 1, but I could have 2, I could have 3, could have 4. Does that make sense? Okay? When I use the phrase exactly 1, absolutely no question how many I have. There's no ambiguity there. There's no debate that there could be 2. Okay? There is 1 and only 1 line. Is that all right? And that's very important, and it's important throughout the entire year and a lot of things that we talk about. And I think I talked to you guys yesterday about making definitions kind of your own. Same thing with postulates and theorems. Try not to, if you make them your own, you can't leave out phrases like that. Okay? Because it becomes an issue later on. All right, so I'll go back to that if you don't have it written down yet. Let's look at this. If I've got these 2 points, A and B, okay? What that postulate is saying is no matter where I move A in relationship to B, or no matter where I move B in relationship to A, there's never going to be a second line that pops up. Okay? There's only ever going to be just the 1 line that goes through them. Okay? And that's why last year when you guys were doing this stuff, okay, you're graphing those, okay, and you did a chart to find x and y 2 times, or maybe you did your y-intercept and applied your slope, then every single one of you got the exact same line, right? Okay? Because every single one of you developed the same exact 2 points, and through any 2 points there's only 1 line. Okay? So that's a pretty key postulate for this course. Now, we can't prove that. The pictures are not enough of a proof. Okay? Showing a demonstration is not enough of a proof. And I'll show you what I mean by that down the road when we actually get some statements that we can prove. That'll be a couple days from now. It'll make more sense on why we can't prove it. We don't have anything. This is the first fact that we have about geometry. So there's nothing before that we can use to prove it. The second postulate we're talking about is that if 2 distinct lines intersect, and they intersect in exactly 1 point. If 2 distinct lines intersect and they do so in exactly one point. Again, the key thing here, got the phrase exactly one. There's something else here. They have to be distinct. If they're not distinct, this fact does not exist. Okay? You guys know what it means to be distinct? Okay? Distinct means that you have two things or three things that are different. They're not the same. Okay? So I gotta have two lines that are indeed different. Okay? And if that's the case, again, going to a picture of this. Okay, if I look at point E there, that's the intersection point. Let's see if we can make it different color than everything else. Okay, that point E, as I move these two lines, as I make these lines change, okay, will that point E ever be like two, well, I guess, will a second point ever show up or develop? No, it can only be that one point. This mouse doesn't work very well. Give me a second. So when two lines intersect, two distinct lines intersect, you're going to have only one point of intersection. Remember last year when you guys would have graphed two lines on the same set of axes? And you're looking for this ordered pair of E with systems equations, and you would have found, if you look over on the left-hand side, it says 9.78 comma 1.1. That's the math you would have found. Okay? Everybody got that same answer. Nobody got something different, and that if they did get something different, they weren't right. They were wrong. Okay? Because when two lines intersect, you get one and only one point. Okay? And that's when they're distinct lines. Here's why we have to have that phrase distinct. What happens at point, let me set it up this way. All right, so you got that red line and that black line, right? If point C lands on top of point A, and point D lands on top of point E, how many times now do those two lines intersect? Infinite, yeah. They're always intersecting, right? Okay? So, when we talk about lines intersecting, we want to kind of eliminate this situation because it provides us some issues, okay? So that's why that postulate says they have to be distinct. Because right now, those two lines, and if you kind of look at now, they're not exactly the way, or exactly on top of each other because of the programming that I have to do. But look at these. That's about 4.3, right? 4.3. 4.7, 4, it's around 4.8, 4.8. And then this number over here, they would be the same, okay? So the equations were the same, right? Does that make sense? Okay? So those have infinite intersection points, and we don't want that to be a situation here with this postulate. So that's why that phrase distinct has to be in there, okay? Because if I ask this question, and I might ask this question, if I write true or false, if two lines intersect and their intersection is exactly 1 point, that's a false statement, okay? Because, I'm going to write this again, if two lines intersect, then their intersection is 1 point. That's false, because right there, I have not taken into account the possibility that the two lines are on top of one another. Okay, or that they coincide. All right, I took one word out of that, right? And it changes the entire way we think about it. And that's something that we got to be careful with throughout the whole system of mathematics. When you're provided information as facts, and you start to change and manipulate and delete words and add words, you could be potentially changing the way we interpret it. Okay, and that's very, very, very problematic. Okay, you guys ever heard the phrase, say what you mean what you said? And that's kind of what we're talking about here. Okay, what is written is what we are saying. We don't want to add anything to that, take anything away from that. All right, we're going to view it just the way it's being stated. That last postulate says if two, again, distinct planes, so they have to be different, they can't be the same one, they can't be overlapping each other. If two planes intersect, then their intersection is exactly one line. Okay? Two planes intersecting has to be one line. As we go through postulates, theorems, even definitions, I think it's a good practice for us to talk about, images of that, okay? And say, okay, this is what we're talking about here. And then show you what we call counter examples of that. Things that somebody might initially think would work, but then explain why it's false, why it doesn't work. Does that kind of make sense? Okay? Because if you can do that, it makes some of our procedures later on a little bit easier to mess around with. All right, so I'm going to show you what we're talking about there. Okay? And I think I maybe used this a little bit the other day with you guys. Those two red and blue surfaces we're going to consider planes. Now they're going to extend forever in the directions that they're oriented. Okay? But they will not gain any thickness. And what I mean by that, when they won't gain any thickness, because somebody asked this the other day. Maybe I already talked about it with you guys. If I look at that, kind of that way or along that, okay? At some point, that little orange plane is going to disappear in that program. I'm not going to be able to see it, but it's still there. And the reason I can't see it is because it has no thickness. Does that make sense, everyone? Okay? So, they're not going to kind of expand like in this direction or kind of this direction down here. Okay, they're not going to become thick like solids. All right, they're going to extend in the directions that their sides are kind of oriented. Okay, so when I expand it, that's kind of the only directions it will extend. So we got these two planes. I'm going to move these planes around, and these sliders will help us do that. Let's see, move it down. Okay. So the way I like to view that, maybe that's the wall in front of you guys. The red one's the wall in front of you guys where the smart board is. Okay. This blue one is the wall to the left where the whiteboards are. So if I make that one grow a little bit, okay, and let's move that one along the red axis. Move this red one a little bit closer to us. You can see that when they crossed, that black line showed up, right? Okay, and that black line is kind of indicative of the corner where the walls intersect, right? Where the walls meet. Okay, if I'm using rectangular walls, and I guess it doesn't really matter whether they're rectangular or not, as long as they're flat, my corner will always be a line. There's no other way that it can happen. Okay? Whenever two flat planes, and that's kind of redundant because by definition a plane has to be flat. Whenever they intersect, their creation is a line, or they intersect to create a line. Okay? Is that something we can understand? I want to show you an example of something that would violate that, or some people might think, well, why doesn't this work? Okay? If I look at maybe it makes more sense to do this. Okay, look at that plane right there. And then I'm going to put in, we'll go back to this one. Okay. Do you see where those two curves, or surfaces, I guess, intersect? Okay, let me orientate this the best way to see it. Maybe, I don't know, maybe like that. You see how it's kind of a parabola where they intersect? Okay? If I get an intersection of surfaces, and that intersection is not a line, okay, then those two surfaces, one or both of them, cannot be planes. Because we have a postulate that says that they have to intersect at a line, right? Okay? And that parabola of intersection right there, if this curve right there that my cursor is tracing out, that is not a line. Okay? By definition, lines have to be straight, right? Is it okay with everyone? Okay. Let's see here. All right, so this brings us to our last postulate and be done. It says 33 non-collinear points. There's exactly one plane. And this is kind of reiterating what we've already kind of talked about. Remember yesterday I had people hold hands up, and we asked if I could set a plane on those hands. All we needed were 3 hands, okay? Because no matter what 3 points we use, there is a plane that contains them, or it goes through them. But as long as those points are non-collinear, there's going to be exactly one plane that goes through them. Exactly one plane that goes through them. All right, so what we're referring to here, okay, through any 3 non-collinear points, there is exactly one plane. If I go back to, this image here, get rid of that, okay? And I think I showed you this at the beginning. If I click on those 3 blue points again, that exact same plane is going to come up no matter how many times I do that. That is the only plane that can be created. And if I move those 3 points, maybe I move A, can you see if that plane adjusts with? If I move B, maybe I move B to the left, the plane adjusts, okay? That is the only plane that's going to go through those 3 points, okay? That means I get exactly one plane through 3 non-collinear points. The discrepancy comes when they're collinear. What happens when they're collinear is something like, and I showed this yesterday, is this situation. Okay? H, J, and I are collinear points. Okay? And when I look at those and I use those collinear points, There's a lot of different planes that can go through those. Does that make sense? You got that purple one, you got that green one. That's just two of the infinite planes that go through them. Is that all right with everybody? And that's the key. That when we start using words like, or phrases like through any 3 points, there is one plane, that's a false statement. Through any 3 points, there is one plane. Through any 3 points. Because we haven't decided whether are those points collinear or non-collinear, and we haven't said whether we have, when I say one plane, we haven't been very specific that, could that mean 2, could that mean 3, could that mean 4? Does that kind of make sense? So that's why our verbiage is very important. I want to do one example that you guys have seen if you started the homework to kind of reiterate this idea of being specific with our wording. It was an always, sometimes, never question. It said, J, okay, Ray JK, and maybe Ray JL are always, sometimes, never the same ray. Okay? When you do questions like this, and you know, I try to draw a comparison to like algebra 1, maybe 8th grade math. When you're doing those types of questions, usually you're given a procedure. You say, okay, I do step 1, do step 2, step 3, step 4, and I get an answer. And I can repeat those steps over and over again and get back to a similar answer for different questions. You can't do that in geometry, okay? Geometry is kind of a fluid type thing where there may not be a predefined process that works you through a lot of the problems, okay? That is one of the issues that people have. So with questions like this, always, sometimes, never questions, you got to think about all potential possibilities, which is hard, okay? And I think seeing examples will be helpful. What point do these two rays have to share? Look at their names. Got to be J, right? Okay. So they both share J. Let's say that K is over here. That's Ray JK, right? L is another point, and they don't tell me anything about where L needs to go or where it could go. So let's say that L was there. Would that be Ray JL? Are they different rays? Okay. What if L was there? Is that any different of a description than what we already had? No. So the fact that L was there or there still gives me the same end result. Even if L was down here, even if L was over here, if L is over here, is JL and JK, are they different rays? So L could be any of these points. On top of JK, on the bottom of Ray JK, to the left of Ray JK. And I'm getting this situation that, yeah, they're different. Okay? But where's the one place that we haven't talked about where L could be? And this is where people overlook things. There is absolutely nowhere in this description that say L has to be up here or over here, here, down here. So because there's no description where L has to be, could it be there? Now is JK and JL the same ray? So we've got a situation where we saw, yeah, it was working a lot. Now I got a situation where no, they're not the same ray. So we got situations where it works sometimes and works, or it doesn't work other times. What do I choose here? Sometimes they are the same ray, sometimes they're not the same ray, right? Okay. Let's say that, let's change the description a little bit. Let's say JK and L are collinear. If they're collinear, J, K. If they're collinear, don't they have to be on the same line? So maybe L's there, right? Or L could be maybe there. So some of us will think, well, this is always going to be true, right? But if they're collinear, then that means that L could be on any portion of the line that JK came from. So the other portion of the line that JK comes from, or the ray JK comes from, is over here, right? So L could be over here. Now is ray JL different than ray JK? So adding little phrases like that could change the way I think about the way I visualize the problem. This is still the way I've got this. This would be a sometimes question or answer. If I put non-collinear here, if they're non-collinear, that means L cannot be anywhere on that ray or the line that ray came from, right? So L has to be there, maybe up there, and that would mean that they are never the same ray, right? Little key phrases like that, even though when we read them, we don't pay a whole lot of attention to them, okay? Because they're small details. They play a huge role, okay? The assignment that I opened up yesterday, not due until class starts on Tuesday. Have a wonderful weekend.